Hello and welcome to the 2023 SMA Interferometry School. My name is Shelby Schimpf. I am a telescope operator with the SMA. I have been with the SMA. I was a summit-based operator for 5.5 years, and for the last 13 years, I've been the lead operator and second shift coordinator for our Cambridge office here in Massachusetts. So thank you for attending the school, and we look forward to seeing you guys here in Cambridge in a few weeks. This talk is going to be a brief discussion about generating your observing script for your upcoming observation. Okay. So let me share my screen. All right, observational planning, creating your observing scripts. Okay, so your proposal has been accepted for the SMA school. What do you need to do now? You need to create an observing script. This talk will go through using the script generator and the SMA Observer Center to create your script. We'll go through the mechanics of what the script actually does, and then we'll give you a couple tips and hints for creating your scripts. So the general script format for the SMA, all of our observing scripts are in Perl, and that is created directly from the script generator. Okay, we have an initial flux and bandpass calibration. It'll then go through the science target loop and go through your different gain calibrators and your science targets. And then we'll have a final flux and bandpass calibration. Scattered within those parts of the script, we also have automatic pointing, and we'll discuss the option of transit calibrators as well. So when you log into the SMA OC, the Observer Center, you will see in the left-hand column, there's a My Projects tab. Clicking on that tab, once you've logged into the Observer Center with your account, you will get to My SMA Projects. This will show you a list of all of the projects for which you are PI or co-I for SMA observations. For the basis of this talk, I am a PI on one observation. And if you click on that code, the code right over here, it will bring you to the summary of the tracks. So depending on your observation, some projects are allocated one track, some projects are allocated a handful of tracks, 2, 3. Some of our larger scale projects will be allocated, a dozen or more tracks. Here you will see a list of all of the tracks for your particular project, and you will see a list. You'll need a separate script for each track that you need to observe. So one takeaway that I want you all to come away with from this talk is you won't get data if you don't have an observing script. Okay, so make sure you get your observing scripts in. So here it shows the status of my project. It's in the scheduling status, but it needs a script. It won't get observed without an observing script. So if we click on Track Overview and Script, this will bring you to this page. If I have a script already in place, I'd be able to see it here and make adjustments. But as we've discussed, and as is the topic of this talk, I don't have a script yet, so we need to create one using the script generator. This information about the track is all propagated in from your proposal, and so you don't have to worry about changing any of that. So when creating your script, there's a bunch of tools available to you. You've probably seen most of these tools when you did your proposals for the observing school or for the interferometry school itself. These tools can all be found here, up here in this tools link. One of them is this passband visualizer. We also have a link to the SMA Calibrator list for planetary visibility tool and some other things as well. Throughout the school, there will be multiple discussions on these tools. There'll be talks dedicated to them themselves. But for the point of this talk, I just want to point out that these tools are available to you. Okay? And like I said, most of you have probably looked at this one, at least cursory glance at it when you were proposing for the school itself. Okay. So on that previous slide, if you clicked on the create script using script generator, you'll get to this page. This information is propagated from your proposal itself. You can adjust the phone number and the email if you decide you want to have a different contact information when you're to be contacted at while your script is being observed. Okay. For the SMA, we observe dual frequency observations all the time. For a typical observation, you will do two different frequencies. So we have receiver A, which is either the 230 gigahertz receiver or the 345. And we have receiver B, which is either the 240 gigahertz receiver or the 400 gigahertz receiver. Most observations, if they're just standard observations, will use two different tuning frequencies, so you get, a wider range of frequencies to observe during your track. If you're doing a polarization observation, these receivers need to be tuned to the same frequency in order to get the proper cross-polarization observations. Okay. So here's where, and with your project, you will be allocated time for a particular frequency band. Here's where you'll specify the specific frequency that you wish to observe. Okay. You'll specify what sideband you want to use, the chunk you want your line centered in, and then any offsets that you needed. Again, here's another link to that passband visualizer to give you more information about tuning frequencies. When we get down here, this is going to be kind of the guts of what you want the script to do. Integration time will default to 30 seconds. Rarely, but sometimes, but rarely do people want to do longer scans. The typical scan length for an SMA observation are 30-second scans. Polarization tracks will use shorter scans, usually 15 seconds or so. If a person is doing a multiple pointing mosaic, they might use shorter scans, maybe a 10-second scan. But typically, it's either a 15 or a 30-second scan for most observations. Okay. I was allocated time in this proposal for one target source, so I'm going to specify one target source here. Here, you're going to specify how many gain calibrators you want to use. For the use in this project, I'm going to use 2 gain calibrators. You can specify the number of flux calibrators you want and the number of bandpass calibrators or passband calibrators you want here. I was allocated time in this project for compact, so that will automatically propagate here. Okay, so this is what, kind of the general bones of what the script is going to be. On the next couple of pages, we'll talk about specifying the actual sources that we're going to observe. Sometimes you might need advanced scheduling observing options, which are listed down here. So if your science source is one that's a very large source and won't necessarily fit in this SMA's field of view, you might need to use different pointings or multiple pointings to get a full observation on the one particular source. If that's the case, the scheduler asks that you use the mosaicing tool, which you can find right down here. So with the SMA, at 30-second scans, what we're doing for this observation, every 30 seconds we get a new scan. When we're changing sources between science source to a calibrator or vice versa, the scans, when the antennas are moving, will get flagged bad. It's those scans also where we calibrate our system temperatures by putting the ambient load in the beam. So we calibrate the system temperatures in between each source, during each source change. If you're doing a mosaic and you just list the mosaic pointings as different target sources here, you're going to end up getting those, at least one scan, if not 2, flagged bad because we'll calibrate the system temperature in between each of those sources. If you use the mosaicing tool down here, it won't do the T-sys in between each of the mosaic pointings. It'll just go one, pointing to pointing to pointing, and only calibrate the T-sys between the last source and the calibrator, and between the calibrator and the next source. It might not seem like a lot, but if you're doing 30-second scans, and if you have a large mosaic, say even 7, 8, 9, 10 sources, if you're losing one scan in between each of those pointings over the course of an entire track, that off source time starts to add up, and you're losing a lot of time in between your sources. So if you do have a larger source that you need to do a mosaic observation with, we recommend that you use the mosaicing tool down here. And if you specify the number of targets to mosaic, you'll be able to specify the different pointings on the next page. Also, with observations, some people get allocated time for 2 different sources in one track, and those sources are separated on different parts of the sky. rather than take the time to like calculate exactly, when it's going to rise, when it's going to set, and do a lot of specifics in calculating your observing script loop, you can just specify that you want to do 2 different loops. So if you have one source that rises early, you can follow that loop, that source for a while, and then you can do a second loop on a source that rises later in the night. So if you specify multiple observing loops during your script, you would do so here. And those observing loops will be done by LST. So that's when it helps if you have 2 different sources that are rising and setting at different times. You can do that using observing loops. Okay. So if you have your integration time, your number of targets set properly here, you can click on proceed and it'll take you to specifying the actual targets. So there will be multiple mentions, a lot of discussion on calibrating SMA data. There's going to be a talk about calibrating SMA data, but many of you may not know how to choose your calibrators. So right now we're just going to touch briefly on the different types of calibrators that were discussed on the last page, but you'll get more information during the school itself. So when we talk about passband calibrators, they might also be called bandpass calibrators. These calibrators correct for the structure from the FI system or the IF system, and also to first order the atmospheric absorption features, ozone, water, things like that. Choosing these calibrators are usually strong, compact sources, bright quasars, things like that. That's what you'll use for your passband calibrator, like strong known sources. Flux calibrators are used to scale the visibility data. These are typically solar system objects: Callisto, Ganymede, the moons of Jupiter, Titan, the moon of Saturn. Those are the type of sources we use for flux calibrators. And lastly, you'll have to choose gain calibrators. Gain calibrators remove the instrumental and atmospheric phase variability during your scans. They're kind of similar to standard stars or during optical observations. And those are usually bright point sources that are relatively close to your science target. When you're choosing your gain calibrator, again, there'll be more talks during this actual school about choosing gain calibrations. But during this, just keep in mind that you want something relatively close to your target source. In that tools option on the SMAOC, there's a list called the SMA calibrator list, and it allows you to specify the position of your target source, and you can sort the list and find the calibrators closest to your target source based on position. Okay. You also want something that's bright enough to be detected. And so if you're not sure if it's going to be bright enough, or you just, if the ones that are very close to your source, you aren't sure, they're rather weaker sources, you might want to consider a second or even a third safe calibrator. This would be a quasar that's maybe further away from your science target, but is known to be bright enough to be detectable. Okay. The second or third calibrator, you can use, you can observe at every loop, you can observe at every second loop. It just depends on how you feel you want to do your calibration. And how often you calibrate depends on the calibrator brightness and the configuration that the array is in when you do your observations. Just remember, when in doubt, calibrate more often. It's always better to have maybe a little bit more calibration during your science loop and lose a little bit of time on science target than it would be to not have enough calibration and not be able to calibrate your data. You'd essentially be losing your entire track. So when in doubt, calibrate more often. Okay. So now back to the script generator. So we just came from that last page where we determined how many of each calibrator type we wanted. This is the page where we actually specify which calibrators we want to use. So I've been allocated time for one science target. For clarity in this talk, I'm just going to call it science target, and I'm going to specify an RA and declination. And remember, there's a hint down here. Make sure the target name is spelled right, and make sure there's no extra spaces either beginning or at the end of your target name. That can sometimes mess up the script when it's actually running. And also proofread that your coordinates for your science targets are correct. I've been operating for a long time, and I know a couple of different tracks that the PI swore we should have detected the source, and we just didn't in his data. And turns out the coordinate for the science target was wrong, and we weren't actually looking at the target itself at all. We were off the target. So make sure that when you specify the coordinates for your science target that they are correct. Check it and double check it. Okay, so here we have the science target, the name of the target, the RA and declination, and this is where we specify how many scans we want to do each time we go back to this target. For the case of this observation, we're doing 30 scans at 30 seconds per scan. 30 seconds per scan, this is going to be 15 minutes on this target. Okay. Down here is where you specify the gain calibrators. Here you can search for gain calibrators based on the source of your, the coordinates of your source. But here you can specify which gain calibrators you want to use and the number of scans on each. Again, proofread. Most of these calibrators are in most of the calibrators you're going to use are in our source catalog. But if you would mistype them, it's going to cause an issue with the script, and you're not going to get your calibrator observed. And if you forget to put the number of scans in, it won't observe it either. So again, just proofread and make sure it's specified to what you want it to do. Down here is when you actually give what you want the script to do. And this is actually where you type it out and specify what the script will do while you're observing. So what I decided to do was do 3C273, the first gain calibrator. I'll go to my science target, the second gain calibrator, and then back to my science target. So that will consist of one loop of my observing script. Okay. If you have multiple targets, you would work them into this. You might do gain cal 1, target 1, gain cal 2, target 2, and then repeat that again. And then you can put, a safety calibrator in there as well. Whatever you want your science script to do, this is where you specify that. Okay. And then down here is where you specify the additional calibration outside the main loop. Okay. So your flux calibrator, as we said, they're normally solar system objects. I've specified Titan and Callisto, and I want to do 20 scans on each. So with 30 seconds per scan, that's 10 minutes on each of those flux calibrators. Don't be too stressed out about picking a flux calibrator. One thing about SMA observations, with our Q observing, it might be a couple days, a couple weeks, it might be a month or so that you submit your script ahead of when your project will actually be observed. So if you specify, if I, like in here, I say I specify Titan and Callisto in my script, by the time my script is observed, one of those may not be available. They may be too close to their planet. The planet itself might be within the sun avoidance zone and unobservable. Don't have to worry about that, because one of the jobs of the scheduler is to check the script that he's planning to run that day and make sure that the flux calibrators are available and optimize the script for the most optimal time frame during that night. So he'll make sure that the flux calibrator that you want is available, and if it isn't, he'll make sure you get a flux calibrator of some sort. Okay. And then when we come down to passband calibrator, again, these are usually strong, bright quasars. I'm going to specify 3C84. And also with the scheduler, he'll optimize your passband calibrator to make sure we get the most out of the nights observing. So if your science target is one that is rising early, he'll make it so that we get on the science loop right away, and then he'll put all of the flux and bandpass calibration at the end of the night. If your science target is one that rises later in the evening, you'll front load the script with all of this additional calibration, the flux and bandpass. So then we get that all out of the way and done, and then we're ready to go onto your science target right when it's available. And then we can follow that for the entirety of the night and get you the most on source time. Okay. A couple other things to take note of on this page: a transit source. The upper elevation of the SMA is 83 degrees, and that's set in the scripts. It's in the subroutines of the scripts. So if you have a science source that goes above 83 degrees from the when observed from the SMA, you'll want to specify a transit source. Okay, because once the source goes above, your science source goes above that elevation limit, this gives the array something to observe during the time until the source comes back down below the elevation limit. People will use this to get additional flux calibration, additional bandpass calibration, But whatever you want to be observed while your source is above the elevation limit, that's what you specify here. My particular science source doesn't go above the elevation limit, so I don't need to worry about it. And also, we used to have to specify how frequently you wanted to do eye pointing over the course of the night. Now we don't have to worry about that. So all of the SMA scripts have automatic pointing worked into the subroutines. So the script will point shortly after the script is started. It will point 1 hour after sunset. And then during the night, the SMA scripts will point every 3 hours. And then once sunrise comes back up and the sun is up during your observation, the script will automatically point every 30 to 40 minutes at that point. Okay, so you don't have to worry about specifying how frequently you want pointing done. All right, so once you continue from that page, you get here, which is an overview of what the script will look like. So this is a good time to proofread one more time. So again, this is all propagated from the project. This is all the information that you put into the script on the previous pages. The name of the science target here, double check the coordinates. You have the number of scans. Again, we specified 30 seconds integration, so that's going to mean on-source time of 15 minutes. The calibrator. So these are my 2 gain calibrators. I said 6 scans on each of those, 30 seconds. That's 3 minutes on each of those. This is the additional calibration that we discussed, flux and bandpass. Flux here, bandpass here, and then a transit calibrator if you specified it. And this gives a summary of your observing loop. So this is a pretty straightforward observation. It's gain cal for 3 minutes, science target for 15, gain cal for 3, science target for 15. Total time for one loop will be 0.6 hours, so just over half an hour. Okay. So if all of that information looks good, you want to simulate your script. And you can do that by clicking this button. So this time stamp that's automatically propagated into the simulation, that will be for the next night, starting at 4 UT. SMA observations generally start at 4 UT, which is 6 p.m. Hawaii time. So on whatever day you're generating your script, this will be for the next day at that general start of observations. If you know your script won't be observed for a few weeks, you can adjust this. You can adjust this timestamp here, but generally just to make sure it's running, the timestamp that's in should work. Unless, like I said, you know that it's going to be, a few weeks or maybe even a month or so before your script is observed. Okay, so specify the time you want, and then you can simulate the observation. And when you do that, you get to this page. Okay, so this has the output for the script simulation, and then your actual observing script is right down here. So congratulations, you've created an SMA observing script. You can look at this window up here and kind of take a look to see if it seems like it's doing what you think it should do. So this is a simulation of what the operators will see when they run your script. They'll have timestamps of when the commands are sent. You can kind of look to see, this is showing, the 6-second scans is showing we're observing the science target. You can make sure the names look right, that the scans look right, and that, the script actually runs. If it isn't working or if it fails right away, you'd be able to notice that too. Okay. And then here is just the actual script that will be put onto the system when your track is scheduled and when the operators are ready to run it. Okay. And so now if you were to go to your My Projects and click on that project code that we did at the beginning, this is what it would show. Instead of saying you need to put in a script, it would show the script right down here. So up until the time your project is scheduled, you can edit your script. You can do it directly from this page using the Manage Script Directly button, or if you decided what you did just wasn't working and you want to start over, you can delete the script or you can create a new script. If you use this button, it will delete this automatically. So this will tell you, if you come to your project, this will tell you when your track has been scheduled. And if your track is scheduled and the observation has been completed, The dates and links to the observing reports will be down here under observations. If one particular track is scheduled multiple times, if either the weather wasn't good enough or there was another issue and they need to run it again, each subsequent time it's observed will be listed down here in the observations. Okay. So when you're scripting, just a few things to keep in mind: get your script in early. Like I said, you won't get data if you don't have a script. So the best way to make sure you get data is to have your script in. Okay. Your gain calibrators, you want something relatively close to your source that's bright enough to be detected. And if you're in doubt, calibrate more often or add a second calibrator for safety. Flux and bandpass calibrators, make sure you put in things that you want to observe, but if you're worried about them being available on the night that your project is actually observed, don't stress too much about that, because the schedule will make sure you get flux and bandpass calibration. Make sure you simulate your script. When you simulate your script, that will show if there's any typos, that'll show different errors. Just gotta make sure your script is doing what you want it to do. Okay. Proofread. Again, proofread the source names, proofread coordinates, proofread the number of scans you're specifying for each source. Because if any of those are missing, your sources won't get observed and you won't get the data that you want and need for your science. Okay. If you have any questions about the script or the script generator, feel free you can ask us operators while we're running your script. You can email the proposal mailing list listed here, or you can talk to your internal contact at the CFA, AJA, or IFA. And for cases of the school, use the Slack channel and you can get information that way as well. So I want to thank you very much for your time, and we look forward to seeing you all here in Cambridge soon for the SMA school. Take care and have a good day.